Guido for almost 25 years, and we spend a lot of time to try to study the problem of neutrino masses and neutrino mixing angles. And today I will speak about neutrinos, but I will not focus on our work, precisely for the reason that Fernando showed in one of these of his slides. We have not a conclusive theory for neutrinos, or in the words of Guido, we have not a baseline model for neutrinos. I prefer to insist on more basic properties. And so I have organized the lectures in two parts. A first part in which I will describe the data about neutrinos, and most of the information we have today on neutrinos comes from the discussion of neutrino oscillations. And the second part in which I will describe the implication for the physics beyond the standard model. So let me start by reminding you the formalism of neutrino oscillation in the simplest possible case, neutrino oscillation in vacuum. Two flavors. We have only electron neutrinos and mu neutrinos. This is the typical experimental setup. We have a source where neutrinos of a given flavor are produced, for instance, electron neutrinos. They travel a distance L, and then here we have a detector where, for instance, the electron survival probability is measured. The probability that a neutrino that was originating here as an electron neutrino is detected here again as an electron neutrino. Now, you know, this is familiar to you also from the case of quarks, that flavor eigenstates are not massive eigenstates. So from the point of view of quantum mechanics, they are not eigenstates of the Hamiltonian. There is a transformation between these two sets of states. And in this case, we have a unitary transformation that is parameterized in terms of a mixing angle, theta, and a phase, alpha. And it is an exercise in quantum mechanics to show that the expression for the survival probability, PE, we are looking for, is this result here. We have 1 minus a typical oscillation term, in which the amplitude of the oscillation is controlled by theta, by the mixing angle. We have sine square of 2 theta. So when theta is 45 degrees, we have the maximum value of this term, of the amplitude. And then we have the argument of this oscillating function, which has this typical structure, delta m squared, that's the difference between the neutrino square masses, times the length over 4e, the energy of neutrinos. We know that in neutrino physics, this delta m squared is extremely small, and so to see an effect, we need both a large angle theta and also this ratio L over E is sufficiently large. From this expression, you see that we can distinguish three regimes for oscillation, depending on the value of this combination delta m squared or L over E. We can have this quantity much less than 1, and then the survival probability is close to 1. Or we have this quantity much bigger than 1. In this case, from the source to the detector, we will have many, many oscillations, and it makes sense to average this oscillation to sine squared to 1/2. And we have this expression for the survival probability. Both the first expression and the second expression do not depend on the energy. They are energy independent. Or the most interesting case is the one in which this argument is close to 1, and in this case the survival probability retains the full dependence on energy. Also, you see, it is useful to remember that if delta m square is 1 eV square, if the length is 1 kilometer and the energy is 1 GeV, this combination is close to 1, from which you can estimate the sensitivity to delta m square of a different type of experiments if you want to be in this energy dependent region. And here you have some example. For instance, for atmospheric neutrinos, you have electron muon neutrinos or antineutrinos produced in atmosphere. The important length is the Earth diameter, as we will see in a moment, 10 to the 4 kilometers. The typical energy range is between 1 and 10 GeV. And so in this type of experiment, you are sensitive to a delta m square of order 10 to the minus 4, 10 to the minus 3 electron volt square. In the case of reactor neutrinos, reactor produce electron antineutrinos with a typical energy of an MeV scale. And we have most of the experiments that have a typical length of about 1 kilometers and that are sensitive to a delta m square close to 10 to the minus 3 electron volt square. We have a single experiment in which the length is of order 100 kilometers, and so you have a sensitivity which is 2 order of magnitudes down, 10 to the minus 5 electron volt square. In the case of the sun, if you neglect matter effects, you have a much longer baseline, and so you are sensitive to much smaller delta m square scales, possibly down to 10 to the minus 10, 10 to the minus 11 electron volt square. Then this formalism can be generalized to the case of three-flavor neutrino oscillation. Here you have the expression for the conversion probability in the general case of n neutrinos. By the way, when alpha and beta, these two indices are different, you speak of a conversion probability, and the corresponding experiment is called an appearance experiment. When alpha and beta are equal, you call this a survival probability, and the corresponding experiment is a disappearance experiment. Now, without going into the details of this result, let me make some comment. This expression refers to the probability for neutrinos. If you want to recover the probability for antineutrino, you simply have to send the mixing matrix U into its complex conjugate in this formula. And you see, also looking superficially at this result, that the first two terms are invariant under this transformation. So the only term in this expression that is sensitive to CP violation is this last term here, which is controlled by this combination of elements of the mixing matrix, which is familiar to you from the quark case. It's the Yarskog invariant. Also, it's a consequence of CPT, which is automatically implied by this expression, that the survival probability for neutrinos and for antineutrinos are equal. And this means that in disappearance experiments that measure only survival probabilities, you have no sensitivity to CP violation. You may also notice that this result is invariant under a rephasing of the mixing matrix, an independent rephasing for each row and for each column of the mixing matrix. And this helps you to count the number of independent parameters this conversion probability depends on. In the general case of n neutrinos, you have n times n minus 1, which is 6 for the physical three-flavor case. We will see in a moment what are these 6 parameters. We need also some convention. These are the conventions that are used in this field. We have 3 masses, and we choose by definition the second mass larger than the first mass. And also we declare that the first 2 levels are the closest ones. So delta m squared to 1 is smaller than the other delta m squared. And with this convention, we are left with the 2 independent physical different possibilities. One is called normal hierarchy or normal ordering. We have the 3rd level at the top, or inverted hierarchy, in which you have instead the first 2 levels, 1 and 2, on the top. Then we have, as we have seen before in the 2-flavor case, a mixing matrix that relates the neutrino flavor eigenstates with the neutrino mass eigenstates. In the 3-flavor case, this unitary matrix is parameterized in this way. We have essentially a first part that depends on 3 rotation angles, theta 1, 2, theta 1, 3, theta 2, 3. Here the indices refer to the fact that this angle, theta 1, 2, parameterize a rotation in the 1, 2 block, and so on. And also depends on a phase delta, which is the analog of the phase which is present in the CKM mixing matrix for quarks. In the case of neutrinos, we may have also 2 additional phases, alpha and beta here, which, however, for the rephasing property that we have seen before, do not enter the expression for the conversion probabilities. So in principle, you see, we have 9 parameters in the 3x3 case, because we have 3 masses, 3 mixing angles, and 3 phases. But the oscillation probability only depends on 6 combinations. We have seen that we have only sensitivity to the difference between the square masses. So we have 2 independent square mass differences. Then we are sensitive to the 3 mixing angles. And out of the 3 phases, we are only sensitive to the Dirac CP violating phase. And now we can come to the analysis of oscillation data. We are helped in this analysis by the fact that we have 2 small parameters. And I can anticipate that these 2 small parameters are, first of all, the ratio between the 2 independent delta m square. We have a delta m square, if you wish, an oscillation frequency which is much smaller than the other one. And the ratio between the 2 is about 3%. And also we have one of the matrix element of the mixing matrix, which is UE3. And UE3 corresponds essentially to the sign of the theta 1,3 angle. So this is UE3, which is essentially controlled by sine of theta 1,3. And the square of this matrix element is also a small quantity of order 2%. So most of the experiments are only sensitive to the larger delta m square and are not sensitive, at least to the leading order, to the smaller delta m square. So in first approximation, it does make sense to set delta m square to 1 to 0. Okay, so it is a simple exercise to take the full expression I have given you before, to set delta m squared to 1 to 0, and to recover much simpler expression for the various probability that we are interested in. In particular, now we have only one independent delta m squared, so we have only one particular argument for the oscillating function. And if you look to the matrix elements that control the amplitude of the oscillation, what you found is that only the element of the third rod of the mixing matrix are involved. So in this kind of experiments, when you can neglect delta m squared to 1, you are only sensitive to this column, to UE3, UMU3, and U tau 3. If, on top of that, you also go to the other limit, the limit in which you neglect theta 1, 3, so the limit in which you put this UE3 equal to 0, you can see that all the expression of the probability collapse to this expression here, and you go back to the two flavor case. Essentially, the flavors that are involved in this oscillation are only the muon and the tau flavor, and you have the expression for the survival probability and conversion probability that we have seen at the beginning. The amplitude is controlled now by the theta 2-3 angle, which is also called atmospheric mixing angle. And so now we can comment the atmospheric neutrino oscillation. Essentially the collision of cosmic rays with the atmosphere, typically typically protons produce pions in the atmosphere. The decay of pions produce different type of neutrinos, electron neutrinos, muon neutrinos, and the corresponding antineutrinos. And it is possible to measure the neutrinos, and in particular the so-called zenith angle distribution of neutrinos. And here you can see this distribution for electron neutrinos and for muon neutrinos, from which you see that electron neutrinos are unaffected. You see the dots are the experimental results. The continuous line are the Monte Carlo prediction. This distribution is in terms of the cosine theta variable, so -1 means upgoing neutrinos, neutrinos that went through the whole Earth before arriving at the detector. Downgoing neutrino are the neutrinos coming from above. Okay. Instead, for muon neutrinos, you see half of neutrinos are lost. This is the prediction of the Monte Carlo without a neutrino oscillation. And in particular, the missing neutrinos are those coming from below, those that cross the Earth before coming to the detector. So from this, if you now use the expression for the survival probability for the electron channel that we have seen before, this implies that this UE3 should be small. So in first approximation, we can set this UE3 to 0. And for what concerns the muon survival probability, by fitting the L over E distribution, we can find at the same time delta m squared. Delta m squared is of order 10 to the minus 3 electron volt square. And the angle that controls the oscillation should be larger, actually should be maximal. This kind of experiments show that the mixing angle is very close to 45 degrees. And so we start seeing something about this mixing matrix. This is how, in first approximation, the third column looks like. You see that we have a maximal mixing. Certainly, this is not a replica of what we have in the quark sector. This is something completely different from the quark mixing matrix. There are many other experiments with neutrino beams that have been made by men that confirm this result. experiments either in Japan, K2K and T2K, or in USA, MINOS, NOVA. In particular, also the interpretation that we saw before implies that the muon neutrino that disappear should convert into tau neutrinos. And indeed, we have an important experiment, OPERA, that have measured directly, is the only experiment that is sensitive to the conversion probability, the probability that a muon neutrino converts into a tau neutrino. And so far, OPERA have seen 5 events of tau neutrinos produced via conversion of a muon neutrino bin created at CERN and sent to Gran Sasso. This is a result recently released by T2K, in which you find the comparison of the different experiments in the region sine square of the mixing angle delta m square. And you see that the most sensitive single experiment is this Japanese experiment T2K. The corresponding region is this region here with a continuous line. And you see also the precision that have been reached in the determination of these two parameters. Delta m square is measured with a precision of 3%. Sine square theta 23 is known with an uncertainty of about 10%. And this most precise determination is still compatible with the maximal value for theta 23. This aspect of whether or not theta 23 is maximal and possibly understand if there is any deviation from the maximal value is very important also from the model building point of view, because there are special models that have a reason to explain this particular behavior, this particular maximal value, and there are other set of models in which generically predict a large angle without necessarily having a maximal angle. Now, so far we have seen experiments that are sensitive to delta m square close to 10 to the minus 3 electron volt square. And if we want to go down in delta m square, we need a larger L over E ratio. And this has been realized by an experiment, Kamland, that exploited many, more than 70, if I remember correctly, Japanese and Korean reactors that have an average distance from the detector of about 200 kilometers. And for this reason, they are sensitive to a delta m square down to 10 to the minus 5 electron volt square. So if, again, you go back and you use the expression for the electron survival probability in the limit UE3 equal to 0, you find this simple expression, okay? Now, the delta m square which is involved is the smallest delta m square to 1, and the angle is theta 1, 2. And this is the beautiful result of these experiments. Dots, again, are the experimental points. The survival probability as a function of L over E, from which you can really find also with the paper and pen, if you sit down from the position of this second dip, the value of delta m square, which turns out to be close to 10 to the minus 4 electron volt square, a little bit less than that. And also theta 1, 2 is not maximal, but is a large angle. Sine square of theta 1, 2 is equal to 1/3. So this first factor that controls the amplitude is a large factor also in this case. And so you can put together these two information. Theta 1, 2 was the angle that controlled this first row. And so you see Camland tells to you the results about this first row. Sine square of theta 1, 2 is equal to 1/3, so we have this angle and also this angle. We had already the third row, and by unitarity we can close this matrix and obtain this structure, this pattern for the mixing matrix, which is a first approximation to the true data. Okay. There are, of course, corrections to this, because here I'm simply putting some numbers to guide you about the pattern of the mixing. However, this pattern, this specific pattern, is called 3 by maximal, and it has played a certain role also in model building to try to understand why leptons have a mixing matrix close to this form. And as you see, it is completely different from the pattern that we have in the quark sector. In the quark sector, we have a nearly diagonal matrix. Here we have 2 large mixing angles and 1 small mixing angle. I should say that from the historical point of view, delta m squared to 1, the smaller oscillation frequency, and theta 1, 2, the angle measured by Camland, indeed were first determined by solving the so-called solar neutrino problems. The solar neutrino problems means the mismatch between the predicted and the observed value of the solar neutrino flux. And indeed, this was a problem that started much before the Camland experiment. And indeed, people wanted to know exactly how the sun, our sun, worked. And since the nuclear reactions that are inside the sun produce neutrino, they wanted to detect the neutrinos coming from the sun, with the result that since the very beginning there was a deficit between the predicted and the measured value of the solar neutrino flux. This problem lasted for many, many years. There have been many experiments that have been proposed in order to study in detail the problem. Unfortunately, the formalism that I showed you before is not sufficient to describe the result of these experiments, because neutrinos in the sun also interact with the matter inside the sun, because there is a non-negligible electron density. And so we should we should introduce matter effects in order to understand the results of these experiments. However, the results of these experiments are in perfect, almost perfect agreement with the results of Camland. Last topic is theta 1, 3. So far we have set theta 1, 3 to 0, but there are experiments that are sensitive to theta 1, 3. And there are 2 types of experiments. We have experiments that are sensitive only to theta 1, 3 among the elements of the mixing matrix, and these are the experiments that are realized with the reactors with a baseline of about 1 kilometer. Again, we measure with this setup the survival probability for electron neutrinos, in this case electron antineutrinos, and setting delta M2, the smaller oscillation frequency, to 0, in this case is a safe approximation. You obtain this very simple formula that you have already seen in the previous slides, in which again the amplitude is controlled by UE3, so by theta 1, 3, and the oscillation is controlled by the larger oscillation frequency. We have several experiments. Before 2012, there was only an upper bound on UE3 from this show experiment. But now we have a very precise determination of a non-vanishing theta 1, 3. And the value of θ13 is completely dominated so far by a single experiment, the Chinese one, Diabei. These are the result. You see, the sine square of θ13 is indeed a quantity of order 2% with a very small error. This is one of the elements of the mixing matrix that nowadays is better determined. And θ13 is the smallest angle and has a value around 8 degrees. By the way, the value of delta m squared that has been determined by this experiment is completely in agreement with the determination from atmospheric neutrinos or from the other long baseline experiments. You see, the virtue of this experiment is that with this quantity you are sensitive only to this element of the mixing matrix. So you can fix really, you can pin down the value of θ13. But there are other experiments in which instead you measure the appearance probability, so the conversion probability of a mu neutrino into electron neutrino. In this case, there is a mu neutrino beam that comes from an accelerator, and the detector is looking for electron neutrinos that originate from this initial beam of muon neutrinos. These are the two among the experiments that have been measured this quantity, T2K in Japan and MINOS in USA. This, again, is the expression that you obtain at the leading order neglecting delta m squared to 1 for this conversion probability. You see that, again, you are sensitive to θ13, but there is already here, you see the presence of another element of the mixing matrix, T23. Moreover, you can see that in this case, the effects and the correction coming from delta m squared to 1 and from matter effects are non-negligible. And so you should include this into the formalism. And this is basically the result that you obtain. The leading order term is corrected by a term which is sensitive to delta m squared to 1 and depends on the quantity that controls CP violation. And this is very interesting because, you see, measuring these quantities P mu 3, P mu e, the experiment really selects a region in the plane θ13 and delta CP after that you marginalize over the other parameters. This is this wavy region that you see here in the two cases of normal ordering and inverted ordering. And now you can compare this region with the determination of θ13 that comes from the previous measurement, from the reactor determination. And you see that from this comparison there is also an interval in delta CP that starts to be preferred. You see that a value of delta CP around minus pi over 2, minus 90 degrees, is preferred in order to obtain a better agreement between the measurements, these two different sets of measurements. If this will be confirmed, this will be, would be an indication for a maximal CP violation in the lepton sector. And since this year we are starting to see this kind of diagrams that are the equivalent of the unitarity triangle in the case of the quark sector. For the first time we are seeing something similar to a unitarity triangle in the lepton sector. You can understand this structure because essentially you have a kind of circle of allowed values, And the radius of this circle is related to the size of UE3, which is controlled by theta 1,3. And the fact that you have, if you wish, the entire radius is due to the fact that the phase is not completely or purely determined. And depending on the kind of hierarchy you have, normal ordering or inverted ordering, you have different determination for the CP violating angle. And for instance, at 1 sigma or 2 sigma, you start having evidence for a CP, a non-trivial CP violating parameter. So let me summarize this first part of the talk. What we know about neutrinos. We know that neutrinos, we have, first of all, upper limits on the absolute value of neutrino masses. These I have not mentioned, but we have a limit of about 2 electron volt coming from the lab, and a more stringent limit of about ranging from a fraction of electron volt to the electron volt on the sum of the 3 neutrino masses coming from cosmology. And then you have seen how we can reconstruct the sine square of the mixing angle and the 2 independent delta m square. Here you have the result of a recent global fit to the data. Also, we know that with this neutrino oscillation, we have the violation of the individual lepton number. For instance, the muon neutrino, the muon atmospheric neutrino goes in part into tau neutrinos, or the electron neutrinos in the sun goes into a combination of muon and tau neutrinos, etc. And so the individual lepton number is violated. On this side, you have the unknowns. The absolute neutrino mass is not completely known, even though it is well constrained. Also, we don't know yet the sign of the largest delta m square, so we don't know if the ordering is normal or inverted. We don't know the phases. We start having some first knowledge about the Dirac CP violating phase, but the other 2 phases are completely unknown. So we have not yet established a CP violation in the lepton sector. And also, although the individual lepton number is violated in these processes, we don't know if the total lepton number, the sum of the 3 lepton numbers, is violated or is conserved. So, first of all, a non-vanishing neutrino mass is evidence for the incompleteness of the standard model. And in fact, let us go quickly. Why so? Because in the case of the standard model, neutrinos are contained in a lepton doublet, and they have only 2 helicity states at variance with all the other charge fermions that have 4 helicity states. You know that gauge invariant forbids a direct mass term in the Lagrangian of the standard model. Okay, and that the charge fermions got their masses through the Yukawa couplings, but a gauge invariant Yukawa coupling is forbid for neutrinos, and so neutrino is massless in the standard model and cannot account for the phenomena that we have seen before. And so the questions are how we extend the standard model to accommodate neutrino masses. Also, why neutrino masses are so small compared with the other charge fermion masses. We have a gap which is of many order of magnitudes. For instance, if we compare the electron volt scale of neutrinos with the electroweak scale characteristic of the top, And certainly another important feature is the difference between the lepton mixing matrix and the quark mixing matrix that, as we have seen, are completely different. So let's start with the extension of the standard model. How to modify the standard model? Well, the standard model as a consistent quantum field theory is completely specified by three ingredients. First of all, we have invariance under gauge transformation, under local transformation of the gauge group SU3 cross SU2 cross U1, and of course Lorentz invariance. Then the other ingredient is particle content. The standard model contains 3 copies of quarks and leptons that fall into 5 independent multiplets of the gauge group. And it has also one X doublet. And the third requirement is renormalizability, the fact that all the coupling constant of the standard model should have a dimension non-negative in units of mass. This is a technical requirement that allows to eliminate all the divergences that we find in the computation of physical quantities, amplitudes and so on, by redefining a finite set of parameters. Now, the sum of these 3 ingredients leads automatically, with the formalism that we have, to the standard model that, on top of these requirements, also possess an additional accidental symmetry. A global symmetry is B minus L, the difference between the baryon number and the lepton number. Now, since with these ingredients neutrinos are massless, this means that we should modify one or more of these assumptions. So let's consider gauge invariance. Of course, we cannot give up gauge invariance because gauge invariance is absolutely a mandatory requirement in order to have a consistent quantum field theory. Gauge invariance is necessary even to define the Hilbert space of the theory. For instance, in the case of QED, remember that the gauge invariance is needed in order to eliminate the extra degrees of freedom that are introduced for the photon in order to accommodate the Lorentz invariance. So we cannot give up a gauge invariance. Of course, we can extend this gauge group. We can consider a larger gauge group, but doing this unavoidably would mean that we should also modify the particle content. Okay. And so let me go directly to the next point. We can modify the particle content. There are several possibilities. Let me give you an example. We can add 3 copies of right-handed neutrinos. These are fermions that are full singlets under the standard model, SU3 cross SU2 cross U1. And moreover, to mimic exactly what happens in the standard model, we also impose invariance under the global B minus L. We have now to impose it by hand, because if we introduce this set of fields, this is no more guaranteed as an accidental symmetry as it was in the case of the standard model. So with these 2 extra assumptions, now we have 2 more helicity states per each neutrino, and so we can write down a Yukawa interaction also for neutrinos. And we derive fermion masses, including neutrinos, that are parametrically given in terms of the product of the Yukawa coupling tau, times the vacuum expectation of the X. So there is no difference at this level between neutrinos and the other charged fermions. We have an exact replica of what happens in the quark sector. And in particular, we will have also a mixing matrix at the level of the charge current interaction. This will be exactly like the CKM matrix, parameterized in terms of triangles and a phase. Now, a generic problem of this approach, first of all, this is just an example, but this is not the unique way in which we can enlarge the particle content of the standard model in order to get neutrino masses. We have introduced fermion singlets, but we can also do this introducing lepton triplets, fermion triplets, or scalar triplets, or supersymmetric particles. And so we don't know exactly which is the correct way to proceed. Moreover, a specific problem of the previous example is the following. If the neutrinos are so similar to the other fermions and the relation between the masses and the VEV is exactly the same as for the other fermions, we do not understand why they are so light. Of course, we can always tune this ratio between the Yukawa coupling of neutrinos and the one of the top to this small number, 10 to the minus 12. But what we would like to have is an understanding of this ratio and of the reason why really neutrino masses seems to be completely separated from the other charged fermion masses. Here, one example, just one example from one of the many theories that have addressed this problem, why neutrinos are so light in this context. Well, neutrinos can be so light because neutrinos, right-handed neutrinos, can be the only particle, apart from the graviton, that have access to a fifth dimension. The idea is that the world contains now 5 dimensions. The fifth one is compact, is an interval, and all the particles, all the standard model particles, except right-handed neutrinos and the graviton, lives in a 4-dimensional boundary of this state, and the right-handed neutrinos, on the contrary, can propagate along this 5th dimension. In this case, when we write down the Yukawa coupling between right-handed neutrinos and the Higgs and the lepton doublet field, we have the right-handed neutrino that contains a full tower, Kaluza-Klein tower of states, and so we should normalize this Yukawa coupling. The right normalization is 1 over square root of the volume of the extra dimension, and if the volume, in this case the length of the extra dimension, is much smaller, is much larger than 1 in units of some fundamental mass scale, then this square root provides a big suppression factor and can explain why the neutrino Yukawa coupling is small compared to the other Yukawa couplings. Let's go to the second possibility. Can we abandon renormalizability? What happens if we abandon renormalizability? Now, I have been educated in my teaching that the renormalizability was a kind of holy criterion that should be kept absolutely. But today we have a more modern view about this problem. And in particular, we can add to the standard model Lagrangian a set of higher dimensional operators with the requirement that these higher dimensional operators are gauge invariant, like we have seen in the previous talks by Michelangelo and by Riccardo. Now, these operators having a higher dimensionality will bring in the theory a new scale, lambda, and the effect of this new scale will be that when we compute a physical amplitude, then the relative contribution of this higher dimensional operator to the new amplitudes is in terms of powers of the energy over this new scale lambda, if we are sufficiently far from mass threshold. The correction will be of order E over lambda to some power that depend on the dimensionality of the operator. So this means that At a certain point, your amplitude will grow up, but we cannot tolerate that the amplitude grows up. We want that unitarity is conserved, that the probability is not larger than 1, and so the theory cannot be extrapolated beyond a certain energy scale, exactly as it happened with the Fermi theory. And so this is the major difference between a non-renormalizable but gauge-invariant theory and a renormalizable asymptotically free quantum field theory, which in principle can be extrapolated up to an infinite energy scale. But suppose now that this scale lambda is extremely large, is 10 to the 15 GeV, for instance. And we have access to an energy which is much smaller than lambda, which is of order 100 GeV or 1 TeV. Then these correction terms are extremely small. And from any practical point of view, the theory will look like a renormalizable theory, because we will not be able to measure the deviation that are induced by these correction terms. These correction terms are at most of the order 10 to the minus 13, which is a tiny number, but by chance is exactly what we need to suppress the neutrino mass compared to the top mass. So this is a possibility which is worth to explore. And indeed, if we make a list of higher dimensional operator, we find a single operator up to flavor combination that can be built with the field of the standard model, and that is gauge invariant. Is an operator that is made by 2 Higgs fields and 2 lepton doublets. It violates B minus L by 2 units. And after electroweak symmetry breaking, you find that this operator gives rise to neutrino masses. But these kind of neutrino masses are not the same as the ones that we have in the first example, the Dirac masses. Now they are parametrically different because they are suppressed compared to Dirac masses by an extra power of the vacuum expectation of the X over lambda. So you see that this now provides indeed a qualitative explanation of the smallness of neutrino masses. Neutrino masses are small in this picture because the scale lambda that characterize the violation of B minus L is extremely large. How large? We should have a scale lambda which is, as an order of magnitude, as large as 10 to the 15 GeV. You see that from this point of view, neutrinos also are very special because they offer a unique possibility to have access to a scale so large as 10 to the 15 GeV that otherwise is not accessible in any present and probably also future man-made experiment. Now, this dimension 5 operator can represent the effective low energy description of several extensions of the standard model. Let me give you an example. For instance, take again the example number 1, add to the standard model Lagrangian, to the standard model 3 copies of right-handed neutrinos, but now let's not enforce the conservation of B minus L. Okay, that we have imposed by hand before. In this case, the most general Lagrangian that we can write with right-handed neutrinos contains again the Yukawa coupling that we had before, plus a mass term for right-handed neutrinos that is perfectly gauge invariant because right-handed neutrinos are singlet, and it violates B minus L by 2 units. And this is the reason why before we had not written such a term. And now the mass scale which is contained in this term is completely independent from the mass scale which is induced by the spontaneous breaking of SU2 cross U1. So there is no reason why there should be a relation between M and the vacuum expectation value of the X. M can be very large, And in particular, if M is very large, we can be interested in an effective description in which we eliminate, or as we say, we integrate out the heavy degrees of freedom that are related to right-handed neutrinos. It is an exercise to eliminate this via their equation of motion, and with this exercise you obtain at low energy this result, which is precisely the dimension 5 operator that we have seen before, in which, if you wish, the coupling is controlled by this combination of Yukawa coupling for the neutrino and the mass matrix for right-handed neutrinos. You see that the role of the scale lambda, which is depleting the dimension 5 operator, is played now by the right-handed neutrino mass. And this mechanism is what you call seesaw mechanism, or more precise in this case, type 1 seesaw mechanism. Now, we have independent theoretical motivation for the seesaw, and indeed, if you wish, the seesaw is based on two ingredients. We should have a large scale and we should have right-handed neutrinos. Now, an independent indication for a large scale we have from grand unification. Lambda close to the 15 GeV is indeed a scale which is numerically very close to the grand unification scale. The grand unification scale is indicated in a number of extensions of the standard model. In particular, is indicated from the unification of the gauge coupling constant of the standard model. For instance, in the supersymmetric extension of the standard model, the 3 gauge coupling for the 3 factors, SU3, SU2, AU1, meet at an energy of about 10 to the 16 GeV. And this is a generic prediction of grand unified theories, theories in which the standard model gauge group is embedded in a simple group like SU5 SO10. These theories, apart from predicting the unification of gauge coupling and predicting the existence of this large mass scale, are also very useful because they shed light on the classification of the particle, of the particle content of the standard model. We have seen that the standard model contains 5 independent multiplets of the standard model gauge group with funny quantum numbers. We do not understand the origin of these quantum numbers, but lepton and quarks are unified into few multiplets of the GATT group, or in the case of SO10, we can even have a single representation, the 16 representation, that contains a single family of quarks and leptons plus a right-handed neutrinos. So you see, a theory like SO10 contains all the ingredients for the seesaw mechanisms, the right-handed neutrinos and the presence of a large scale, and it brings certainly a strong motivation for the seesaw. This is an extremely fascinating possibility. Unfortunately, so far we do not have an experimental test of this idea. In grand unified theories, there are particles, heavy particles that mediate interactions between quarks and leptons and can convert quarks into leptons. And so, for instance, the proton is no more a stable particle. But on one side, the prediction for the proton lifetime is extremely model dependent, and there are many types of these models, and we do not have a clear prediction. And on the other side, we have so far only experimental lower bounds on the proton lifetime. This is a recent compilation of these bounds. Here, everything is dominated by super Kamiokande. by the way, historically, Super Kamiokande was conceived as an experiment to discover proton decay, and it was only by accident that by studying the background to this reaction, the people working in Super Kamiokande realized that atmospheric neutrinos represented a serious background, and so they started to investigating more and more the atmospheric neutrino, and they ended by discovering neutrino oscillations. The theoretical prediction about proton decay cover a huge range from 10 to the 32, 10 to the 33 that are already excluded for most of the channels, up to 10 to the 36. And so certainly here we have still time to improve the situation and hopefully to find eventually this important signature for this class of models. Let me add two additional virtues of the seesaw mechanism. In the seesaw mechanism, the light neutrino mass matrix is this combination of the neutrino matrix of Yukawa coupling and of the right-handed neutrino mass matrix. And it is relatively easy to see that it is this combination that, starting from small mixing angles, can produce the large mixing angles that we see at the level of the light neutrinos. Let me just flash you an example. Here you see a two-flavor example in which you start from a matrix for right-handed neutrinos that have no mixing at all, a matrix for Yukawa coupling that have a small mixing, and in a suitable region of parameter space, you end up with this combination, which has a maximum mixing. There are many, many examples that can be built along these lines, showing the importance of the seesaw mechanism and the role that the seesaw mechanism can play in order to explain this different feature, large mixing versus small mixing, of the lepton sector. Another important advantage of the seesaw mechanism is that the presence of the heavy right-handed neutrinos can explain the observed matter-antimatter asymmetry, and this can be produced from the decay of right-handed neutrinos in a particular regime, producing a lepton asymmetry that subsequently the standard model interactions can convert into a baryon asymmetry. And indeed, in the seesaw mechanism, the free Sakharov condition can be realized. We have a violation of the baryon and the lepton number. We have also violation of the charge conjugation and CP by the additional phases that are present in the seesaw Lagrangian. And also we can realize an out of equilibrium condition during the evolution of the universe. And it is interesting to see that there are restrictions that are imposed by this mechanism that is called leptogenesis on neutrinos. For instance, the out of equilibrium condition requires that essentially the decay width of the right-handed neutrino is not too large, in such a way that the rate of the right-handed neutrino decay is sufficiently small to bring this reaction out of equilibrium. And this translates into a requirement on neutrino masses. The light neutrino masses, at least in the simplest possible way in which you can realize this mechanism, should be smaller than about 1 electron volt, let's say. On the other hand, right-handed neutrino should be heavy because this baryon asymmetry is proportional through some more or less fixed coefficient to the so-called CP violating asymmetry, and this CP violating asymmetry is directly proportional to the masses of right-handed neutrinos. And so to have a sufficiently high CP violating asymmetry, these right-angle neutrino masses should be relatively high, should be larger than about 10 to the 8, 10 to the 9 GeV. And so again, you find that at least qualitatively, the feature that we find in the data are also reflected or also accommodated by this elegant mechanism. The seesaw has also weak points because the full energy theory is difficult to test. Let's reconsider the second example. No, we have this Lagrangian, but this Lagrangian now contains many parameters. If we count the parameters, we have 6 masses now, 6 neutrino masses, 6 mixing angles, and 6 physical phases. We end up with 18 parameters. And instead, the low energy theory contains, as we have seen, just 9 parameters. Half of them, 3 masses, 3 mixing angles, and 3 phases. Okay. And so it is difficult to test all these extra parameters. We have only few observables that we can exploit in order to pin down the extra parameters. It is much easier to test the low energy remnant, the dimension 5 operator, which however is a universal operator. It does not imply the specific particle content that we have seen in this Lagrangian. Okay. And this dimension 5 operator can be tested by the fact that it violates B minus L by 2 units. So we look for a process in which B minus L is violated by 2 units. And the best candidate to date is the neutrinoless double beta decay, in which a nucleus with Z protons goes into a nucleus with Z plus 2 protons by emitting 2 electrons and no neutrinos. So you see B minus L is violated exactly by 2 units. And this would discriminate neutrino masses related to this operator from Dirac neutrino masses in which we have enforced by hand the conservation of B minus L. Now, more in detail, the decay rates of neutrinoless double beta decay depend on a particular combination of neutrino masses, mixing angle, and phases that goes directly in the amplitude. Is this MEE combination is a weighted sum of neutrino masses by the square of the mixing elements. And with the parameterization that I show you at the beginning, this is the explicit expression. Okay. And now, from the knowledge that we have on the mixing angle on delta m square, we can try to extract from this expression prediction. And for instance, in this plot, you see this mass that is measured in this process versus the lightest neutrino mass. You have 2 regions depending on the kind of ordering that you have. A region related to the inverted ordering and one related to the normal ordering that merge in a single region when the lightest mass is sufficiently high. In this case, you have a quasi-degenerate spectrum. And you see also in this plot the different bounds that have been found, have been set so far by different experiments with a sensitivity which is approaching the region related to inverted hierarchy. On one side, this would be an extremely important experimental result if we were able to isolate this particular decay, because it would provide at the same time evidence for B minus L violation for a certain kind of neutrino masses, and also it would give you some indication about the possible pattern of neutrino masses involved. On the other side, this experiment is extremely difficult, both from the experimental point of view and also for the theoretical interpretation, because to extract this parameter from the experiment, this goes through a computation, the computation of the nuclear matrix elements that are involved in the computation of the decay rate, and there are large errors that affect this determination. In particular, this is more technical. I can go quickly on that, but the largest theoretical uncertainty today comes from the so-called axial coupling constant, and depending on the value of the axial coupling constant that you want to use, the same experiment can provide different bounds that differs really from factors of 2, 3. So you have a large spread in interpreting the results of these experiments. There are many experiments that are ready or almost ready to provide new results and to approach, hopefully, this region of the inverted hierarchy. So let me conclude. The conclusion is much more in line with the sentence that was written by Guido in the conclusion of the proceeding that was recalled by Fernando in his talk. We do not have a theory of neutrino masses, neither for neutrino nor for charge fermions. And here we are lacking something like a unifying principle. And personally, it seems to me that the situation resembles the situation of weak interaction before the electroweak symmetry was discovered. Remember that with the requirement of SU2 cross U1 gauge invariance, we were able to describe the very many fermion gauge boson interaction in terms of only 2 parameters, G and G prime. And here, unfortunately, we have many parameters in the Yukawa sector of the standard model and its minimal extension to accommodate neutrino masses, up to 22 parameters. And unfortunately, so far, we do not have a similar principle that can brings down the number of parameters. There are many ideas and prejudices, but we are lacking, in the words of Guido, a baseline model. And we should also try to be careful, because many prejudices in the field of neutrinos turn out to be wrong when confronted with the experiments. Maybe some of you will remember that we thought that neutrino masses should be around 10 eV because this was the cosmological relevant range, or that the solution to the solar neutrino problem should be a small mixing angle solution, because in the quarks we have only seen small mixing angles. And also at the beginning, people thought the atmospheric neutrino problem had to go away simply because it implies a large mixing angle. All this was wrong, and so we should have new ideas without prejudice. Thank you.